Kia ora koutou, ngā mihi nui ki a koutou katoa, ko Glen Rowe toko ingoa. A very warm welcome to you all. My name is Glen Rowe, and it is my pleasure to introduce the penultimate in this series of live presentations for the 2020 RASNZ online conference. In this session, we have a couple of presentations relating to gravitational wave events. Max Briel is a PhD candidate in astrophysics at the University of Auckland, who will describe how predicting the number of supernovae and gravitational wave events in a synthetic universe could aid our understanding of the evolution of binary systems. If you have any questions for Max, please use the chat function and we'll put your questions to him at the end of his presentation. Over to you, Max.
Hi. Let me quickly share the screen. There we go. I go full screen. Oops. There we go. That should be visible for everyone. All right. Then welcome everyone. Thank you for being here and watching the stream. So I'm Max Briel, as Glenn just introduced me, and I'll be talking about observing transients in a simulated universe. But first, a little bit about me. So I'm Max Briel. I'm a PhD student at the University of Auckland. I did my bachelor's on the evolution of post-main sequence mergers, and my master's on the reconstruction of neutrino events within Came3Net. And besides that, I do a lot of running, swimming, and also some tramping. So you might be wondering, what are transients? Let's quickly introduce the rest of my team, the people I work with as well. Later on, we'll have Jan's, JJ's talks. You might have already seen a few of the faces here, such as Eloise and Petra's. And so these are the people I work with here in Auckland and some of the people I work with in the UK. And we all work on population synthesis, binaries, in the here and now, but also in the old redshift, so far in the past galaxies there. And so then we can continue to the transients. So what are transients? Well, basically, on a long, stars have a really long lifetime, basically in millions of billions of years. Transients, on the other hand, are very short-lived. This can take seconds till, but all the way up to hours or months. And they include quite a collection of events, such as eclipses, gravitational microlensing, supernovae, gravitational wave events, gamma ray bursts, novae, and often some transients. And specifically, the ones I will be focusing on are the supernovae and the gravitational wave events, which basically relate back to stellar evolution, and specifically binary evolution. And these transients, the supernovae and gravitational wave, relate back to the stellar population. Basically, they can tell us something about what, how the stars, such as the binary systems, have evolved, but also how stars have lost their some mass, and also what the situation, the environment was like when they were formed. And so from the transients, we can basically deduce information about the population. But this is a very complicated relationship because for a lot of the systems, for the transients, the origin, the progenitor, isn't necessarily known. And so we can also work it the other way around, where we have a stellar population with a specific environment, and we make some assumptions about the stellar evolution, and then predict how many transients we get. And so diving a little bit deeper into which kind of transient there are, and specifically the supernovae to start with and the gravitational wave after, we'll first have the quick look at the supernovae, which consists basically observationally on two types. Probably quite a few of you know this classification if you've done some supernova observations. That is the type 1 and the type 2, where you basically look at the spectrum and you see that the type 1 are very hydrogen poor, while the type 2 are very hydrogen rich. This is the high up classification that was used quite a while ago. And after observations got better, we basically started to distinguish different types. And so these are the only ones that are relevant for this talk, but there are quite a few more that we can divide in subclasses. So we get, for the type 1, we get type 1As, 1Bs, and 1Cs. And then for the type 2, there are some different classifications, but we'll just keep it for type 2 now. These classifications are purely observational. And so once we started to think about, all right, what were the progenitors of these supernovae, we basically came to the conclusion that some of them are far from the same one, but they don't align with the types. And so what we get is that the 1B, 1C, and type 2 all come from core collapse supernova. That is basically that the star at the end of its lifetime can no longer continue fusion, and it sort of starts to gravitationally collapse and then explodes. Therefore, the core collapse. And this is because it can come from single star evolution. It's especially if the stars are massive, it's a relatively fast process. It can be anywhere from around like tens of mega years, but it can be extended through binary interactions to a few hundred mega years. And so, but it still follows the star formation, so how many stars are born, relatively closely. The type 1As, on the other hand, are a little bit different because they're created from basically, they probably have a progenitor system from white dwarfs. That is sort of a really small star that is electron degenerate. And that white dwarf is accreting mass. It's basically eating up mass from a companion, so it has to be a binary. Until it reaches a certain mass, it at that stage, which is 1.4 solar masses, it just explodes, and therefore it has a sort of very typical, because it's a certain mass, it has a very typical light, and it can be used in cosmology, for example. And so the explosion that takes place here is a thermonuclear explosion. And it follows basically some older star formation, because you first need to create this white dwarf, and then that white dwarf has to accrete material on it from a binary companion. And so this process can take a lot longer than just a single star evolution. Another idea how type 2s can take place is that you have two white dwarfs, and they basically rotate like you would get with gravitational wave events, and they would merge, also creating an explosion. And this would also be a relatively long process compared to the core collapse. And also, therefore, it probes star formation at an older time than the core collapse supernovae do. And so these white dwarfs are basically also known as compact objects, but there are also a few more, which we know from the gravitational wave events. We have the neutron stars and the black holes, and basically they rotate around each other and merge into one, and that's the chirp mass that we measure with LIGO Virgo. These neutron stars and black holes, however, have to be created from stars, and basically have to survive several explosions in between them. And this basically means that the stellar evolution, stellar evolution determines if we get a neutron star or a black hole, but also the binary interaction determines if it survives or not. And so these are components that are important for neutron stars and black holes. And of course, we also have the possibility of having a neutron star and a black hole as a merger together instead of two neutron stars or two black holes. We won't go into those because the constraints on their observations are relatively broad. So for the neutron stars specifically, because they're relatively lighter than the black holes, they're really sensitive to the binary evolution, and in this case, like how, for example, how much is the kick from a supernova explosion on the companion, and does it become unbound, or does it stay bound? The black holes, on the other hand, are more influenced by this metallicity evolution and the star formation, and that basically determines how many black holes we would get. And so we have these two, the supernovae and the gravitational wave events, and that is basically where we can start predicting them. But what do we need to predict these events? Well, that's two components. The first one is basically we need something to describe the stellar evolution. In this case, we'll use a population synthesis, BPAS, which includes binaries, of course. And this is basically describes the how a small population of stars, so this is in a quite detailed manner, how they evolve over time. And we'll get into this as well a little bit further. And our second component is basically the star formation rate. And this is at a larger scale, looking at how much mass and matter is being created at a certain rate throughout the history of the universe. And we can get this from empirical data, but another possibility is using cosmological simulations to basically use the star formation rate from those to predict the events we're getting. And so going back to our stellar evolution for a little bit, this basically works as follows. We get a sort of moment of starburst, that is, we create a bunch of stars with all kinds of initial parameters. We create this according to the IMF and some binary parameters, and we just create them all at the same time for a certain mass. And then we evolve them and basically see what happens to them. So some might explode. Some in some binaries you might get two explosions and you get two neutron stars, or you get two black holes and they merge. And so this is everything. We record everything and then put this in what we call a delay time distribution. And we'll zoom in on this one a little bit more because this is quite essential. It basically describes what happens to the population and what kind of events take place. So, for example, here we have a starburst moment on the left. It's actually a little bit further left than at the 6. And then we have the evolution of the different types. So in blue for here we have the core collapse, which is relatively fast after the starburst. And then in yellow, orange, we have the type 1As, which is something that happens later on, as we said. And then we have the gravitational wave events in black and the dashed line. And so we can see that the distributions are quite different between the different types already. But that is not the only thing. It's also metallicity dependent. And so on the right, we have a metallicity that's lower, and we can see that the binary neutron star is still in here. We can see that the distribution here, especially of the type 1A and of the gravitational wave events, is quite different. In this case, it's actually increased for the black hole ones. For the gravitational wave events. And important here is basically that our event rate is metallicity dependent, which will come into play in our second part for the stellar formation rate. So we've now basically gotten the stellar evolution part down. This basically contains all the parameters for the binaries, for the stellar evolution, and for basically the gravitational wave merger happening. And then we can look at the star formation rate. And so this consists of two parts. The metallicity evolution, that is, of course, all elements except hydrogen and helium. And the cosmic star formation history, that is basically how much stellar material is formed. And we often describe this as a density, which is basically averaged sort of over the whole universe. And this was originally, a lot of this was taken from observations in two kinds of spectra. One was the infrared, where we have some data points and we fit a line to it, and the UV, where we have some data points and we fitted a line to it. And then, of course, we combine it all to get a proper sort of stellar formation history, where basically we have the now on the left side of the figure, and then the older the more in the past is to the right. But of course, this is empirical. This is what we've sort of measured, and we've used models to get here. And so it's also kind of important to include some sort of metallicity connection to this, because this is only describes the amount of matter created at a certain moment in time. But we don't know which metallicity it is. And we saw earlier with the population synthesis that it's really important to know what metallicity it is. So there's certain parameterizations of this, and one of the ones we can use basically just splits it up in several different categories, and that's what we get the following, where we have low metallicities in blue and high metallicity in red. We basically see that in the early universe on the right, we basically see there's mostly low metallicity, and the further we get to the now, which is on the left, we get to higher metallicities. And this is basically what we expect, because supernovae and all kinds of processes within the universe create heavier elements and enrich the environment, and therefore we also get stellar formation, star formation at a higher metallicity. All right, this is just the one we got from the empirical data, but let's have a look at the ones from the cosmological simulations. And so there are three main cosmological simulations that at least I have used in my research. That is the Millennium simulation, the illustrious TNG simulation, and the Eagle simulation. And what you can see immediately is that their shapes are quite different than the empirical one on the left. The black lines are the total ones, and they're quite a bit different. And especially when considering when they start. They start much later, more to the left than the empirical one does. The empirical one starts over on the right, and this one actually, they all are kind of in this regime from around 14 to 15, 16 even for the Eagle one. And so they start much later than the empirical one in the stellar formation. And that is quite important, because it means that in the initial universe there was less formation, or according to the simulations, there was less formation of stars. In the Eagle one, you can see that there's quite a lot of low metallicity production in the beginning as well. But overall, as you can see, for example, with the illustrious one, we have around redshift 8, we have already high metallicity star formation. Similar for the Millennium simulation and for the Eagle one. However, for the empirical one, the really high metallicity star formation only starts around redshift 4. That is a lot more closer to our current time than the simulations predict. And so we have quite a lot of earlier high metallicity star formation, which is important, of course, for some of the events, transient events that we're looking at. And so with these things, with the star formation rate in there, we can start looking at actually calculating the events. So we combine the stellar evolution with the star formation rate, and combining the two gives us a number, like an event density, that we can compare against observations. And so starting with the type 1a, as I said earlier, it follows the older star formation relatively closely. And on the left, we basically have the figure with all the simulations and predicting the events over this, of course, over this age of the universe. And we see that kind of the Eagle and TNG in green and yet orange kind of closer together, and the empirical one from Dow and Dickinson's is relatively up high, with the Millennium one taking over. This on its own gives us already some information, but of course it's far more interesting to compare these against observations. And so here we have a bunch of observations, and because it's very difficult to measure, basically get this into a event rate, there's quite a large errors on them, and all fall within the constraints. The type 1As in general, the shape between the simulations is all the same, and so it's also expected in a certain sense. And we can't really say which one of it is. So it can be any of them. And that either can tell us that our star formation in the early universe is correct, or it is just not, there's just not enough information to say anything about it. But of course, we have multiple events. So we can use another event type to kind of get additional information if we're being correct here or not. And so one that also follows the star formation closely is core collapse supernovae. It only follows it more the more current, so more closely to actually what the star formation is at that age. And once again, we kind of get similar shapes out, but they're a little bit, the Madden-Dickinson one, the empirical one, is far more up than the other ones. And comparing these against observations gives some really interesting results because we basically get the observations going in two different directions. We have the cluster near the Madden-Dickinson line, and we have the cluster, or sort of data measurements, observations down here near the TNG and Eagle simulation one. And so these are from different sources, and so different measurements actually suggest different models. Because there's such a difference between these different models, a really interesting thing here the conclusion we can draw is that basically by performing observations around redshift 1.5, between 1 and 2, we can actually get better constraints on the stellar formation rate during this time and try to select which one of these models is more accurate. With that, we also have two more types where we can actually look at the binary interactions, which is to start the black hole mergers, which is sensitivity to low Mendeley star formation, and the binary evolution. And here we see that the simulations are much lower than the Madden-Dickinson one, and this probably has to do with the low metallicity star formation at the beginning, that there's a lot more low metallicity star formation for the empirical fit. If we compare these two observations, we see that we're far higher up with the predictions, and the actual observations is much lower. It's sad news, but it's also good news because it means oops. Sorry. I think. Yeah. All right. That's what I noticed. This was still clear? This was still there? The observations? All right. Perfect. Oh, okay. Well, so basically what we're seeing here is that we are lower than the observations is much lower, which are down here, than our simulations. And it means that we're basically over predicting it. And this might have to do with that we're still using there's still too much low Mendeley star formation, or it might be into the binary evolutions that we might have to tweak some settings. However, the neutron star mergers are more sensitive to the binary evolution than the black hole is. And so if you compare that against observation, we see that these actually fit really well with our model predictions, with our with the observations and the model predictions. And so this kind of begs the question: Are our binary evolution parameters seem probable in this sense, but on the binary side, on the black holes merger side, it doesn't seem right? And so that might just indicate that we might have to look more into the stellar formation history for the black hole ones. But of course, at the same time, we shouldn't neglect the possibility that our neutron star mergers are still there might be wrong here, and it's two effects. It might just be two effects canceling each other out here. And so we can basically say four different things. Is that type 1a tells us basically that all the models can be possible. The core collapse supernova basically can help us constrain it because there's such a difference between the models. The black hole ones indicate that there might be too much low Mendeley star formation in our models, or it might be that our binary parameters are off. However, the neutron star tells us that the binary parameters might be probable. So we kind of don't know yet, and there is a lot more extra information we can do, and part of that is, for example, we can look at different types, different events, transients. So I've only talked about these now, but there are also parent-stability supernovae. They haven't been observed, but it basically is a really massive star that evolves up to a certain point, and it becomes so heavy that internally the photons start to create pairs, electron-positron pairs. And so this causes basically the radiation pressure to collapse, and the star sort of just explodes and disintegrates. This, of course, hasn't been necessarily observed. This is a theoretical idea, and there might be ideas of what it can be related to, but that's not necessarily the case. A more observational thing is, sorry, that's the wrong way, the long gamma ray bursts, which is basically what it says. It's just gamma rays that we measure, and they take a relatively long time. And these are both very metallicity dependent. And so this can give us another sort of way in seeing, hey, are we doing the right thing with the metallicity or not? The problem here is that the measurements for at least gamma ray bursts are a little bit sparse compared to, of course, the core collapse and the type 1As. For the gamma ray bursts as well, one of the things we can do is also, they're kind of related to type 1Cs, and so we can also start to try to distinguish between even the different subtypes of core collapse supernovae to really hone in on like each different event type and what kind of relation they have with the environment and the binary evolution. And so that will be our next step, basically, trying to hone in on these other events to constrain our cosmic star formation rate and also our binary evolution. And with that, I want to thank you for listening. And yeah, if there are any questions, let me know. Oh, okay.
Okay, thanks very much, Max. We'll just give it a moment in case there is a question to come in.
Otherwise, I will be around during the next talk, so you can drop your question in the chat as well during that time.
Yes, that's great. Thanks, Max.
There we go.
Okay, well, with that, we will move on to the second presentation in this session. This one is by Max's supervisor. So this is a pre-recorded presentation by Associate Professor Jan Eldridge at the University of Auckland. The title of Jan's talk is Understanding the Stars That Create Gravitational Wave Transients. I'll just, oops, share my screen, get the talk up. Oh, hold on. Going to turn on the audio. Sorry, what's that, Steve? You haven't, okay. Sorry about that. Oops. Oh, sorry. Is that better?
Okay. I'm going to be talking about understanding the stars that create gravitational wave events, which are these new window of the universe we have from merging black holes and neutron stars. So I'll first off begin introducing binary evolution, and then we'll get down to how binary stars can produce these black holes and neutron stars in binaries that then can produce gravitational waves that we can observe with the gravitational wave observatories. A lot of this work is done in collaboration with my main collaborator, Elizabeth Stanway from the University of Warwick. And I'm, of course, at the University of Auckland. And part of my funding comes from the Marsden Fund, organised by the Royal Society of New Zealand. I'll talk about the kind of work that we're being funded to do now to study these gravitational wave events. And of course, there's also the very big BPAS team, who I'll introduce them all shortly. Just to introduce myself, I'm Associate Professor Jan or JJ Eldridge, either is fine. My pronouns are she, her, them, they. I'm an astrophysicist, and I study exploding binary stars while exploding them to the gender binary, because I'm transgender, which means my gender does not line with the sex I was assigned at birth, and I'm non-binary, and I don't really fit quite well into the male-female binary that society seems to assume that everyone does fit into. I work, and all I'm just trying to say there is, we're going to learn about how exciting and wonderful and complex the universe is, and it turns out that people are complex too. And, some of you will have seen how I've changed my name and my pronouns over time, and that's just because it takes time to try and understand yourself. So, people are complicated and the universe is, so yeah. In astrophysics, though, I do work on stars, galaxies, supernovae, gravitational wave events, and so we'll try to cover some of all of that during this talk. And you can find me on Twitter at astro_JJE. The BPAS team is growing all the time. So there's me, there's Elizabeth Stanway from the University of Warwick. Then we've got our new postdoc, Hilary Stevenance at Auckland. Lynn and John were past PhD students, now have postdocs around the world. Max and Petra are current PhD students. Max is working on cosmological star formation histories. Petra is studying LISA and white dwarfs within our galaxy. Sohan and Wouter are past master's students and should be starting their PhDs soon. Sean is a current master's student, and Gleb and Edith are both undergraduate students who are working on the BPAS project. And it's just so you get the idea that this project I'll be talking about is a huge number of people who are working together. And of course, it's also built in on the success and contribution of many other past students, both at Auckland and at the University of Warwick. And one important thing to begin this talk with, though, is how to understand how single stars and binary stars are really different in the way that stars evolve. Our sun is a single star, and when we look at the universe, though, that many stars are in binaries. And normally when you're learning about how stars live, especially say in an undergraduate course or in textbooks, they always try and focus on the single stars first. And that's because it's very simple and very simple picture, which is the idea that stars, when they're single, start evolving burning hydrogen to helium. Then you get your helium core, which with the hydrogen envelope still around, because the burning of nuclear fusion is stuck to within the core. And then that will burn on to carbon oxygen. And stars like our sun stop at that phase, and then they lose the hydrogen envelope, which I've indicated in red here, and you end up with just the carbon oxygen white dwarf that goes off. Nothing else interesting happens, it just cools off over the age of the universe. More massive stars, however, can go further burning stages, and you can form an iron group elements core or an oxygen neon core, which can collapse, forming a neutron star or a black hole. And it's very simple. Nothing much else happens really apart from what's determined by the initial mass. If the star is massive enough, it will become called a supernova. If it's less massive, it will just form a white dwarf. And so that gets quite boring, which is also why it's simple. I say it's simple. There are many complexities within the evolution of a single star that I could go on about, and why you do have to talk about it. But it gets worse, because let's say that this single star here had another star, another companion orbiting around it at close distance. And then things get more complicated, because here in the center, we have where we start, we'll have two main sequence stars, but the more massive one will evolve more rapidly. And so it will get big, it will try and become a red giant, but if you've got another star next to it, then they'll get in each other's way. And depending on how close they are, will determine what's going on at the center, what evolutionary phase the interaction happens at, and the mass ratio, whether they're very similar in mass or very dissimilar in mass, will give you some constraints on how severe the interaction will be. And so the situation becomes more complicated, and yet most stars in the universe are in binaries. And of the evolution you can get, sometimes the two stars might merge and produce become a single star. Otherwise, you can actually go through a point where you get your first supernova, and so the system may become unbound, which is where these loops come round, and so the first supernova is over here. And so if this binary becomes unbound, then again, you get a single neutron star or black hole, and a single star that then go on its evolution and produce another single binary, a single black hole neutron star. Whereas if the system remains bound, then you can actually get a star of a black hole neutron star, and when that goes to the end of its lifetime and the other star can explode in a supernova, again, you might get two single neutron stars that fly apart. Or sometimes they may end up staying as two neutron stars or two black holes, and then merging with gravitational waves, which we can detect. So binary evolution gets really complicated. And actually, I'm trying now when I teach this, or teach stellar evolution in undergraduate level courses, to actually try and start from talking about binaries, because binary evolution, in some sense, I'm going to say this is easier, even if you compare the two figures, right? You're thinking like, well, the other one was quite simple, but you can already try and understand binary evolution from a very basic viewpoint. Now this is, so also, as I say here, right, you get many more helium stars. So binary interactions tend to strip off this red hydrogen envelope, right? So most interactions happen after the main sequence when you form this helium core. So actually you can take away all that material off the surface and you form a helium star. Now helium is a much more dense material, at least in a stellar interior, right? Because it's lighter than air in the room that you're in, which is why helium balloons float. But when you've got a star made of helium, it can be a lot denser, so it can be a lot smaller, the same mass, and it can be a lot brighter and hotter. And as I've said here, a lot of work here has been done by Oliver Gottberg. But this higher, hotter, more luminous stars give you a different star that you can't get from single evolution. You can do for the very massive stars because they can have strong star winds. But it's interesting. This is where binaries become most important. If we're looking at the HR diagram, or the Hertzsprung-Russell diagram, which is where we try and work out what the age of most stars are, this is how we show populations of stars together. We can see that so before I was just showing you a rough sketch of what goes on. But here, this is where we can see in the black lines, we've got the single star evolutionary tracks on the HR diagram. So the black lines are single stars evolving over their entire lifetime and how they move in terms of temperature, hot and cold on the x-axis, and luminosity on the y-axis, going from faint to bright. We can see that stars generally evolve brighter and cooler over their evolution. When they're burning hydrogen to helium, they form their helium core and they jump across to become red giants. Very massive stars, they may have very high massless rates, red supergiant phase, and so that's when they come across and become helium stars themselves. So very massive 40, 30 solar mass stars and above can become helium stars on their own. But lower mass stars like 20 or 10 solar masses can't do that. And here we need the binary evolution to be able to produce these lower luminosity helium stars and Wolf-Rayet stars that wouldn't exist without binaries. Now, Wolf-Rayet stars are just a fancy name for a helium star. It's very massive, and so they're like at least 10 times the mass of the sun. Because they're so bright and luminous, they have very funny emission lines, whereas these helium stars are identical, but they're less massive, so they don't have very funny emission lines, so they're not called Wolf-Rayet stars. And you can see here that basically, or one way of looking at this is to say it's a bit of a mess, right? When you have your binary tracks, which are the color lines. So the single lines, star lines in black are very plain and boring. You put in the binary tracks, which are in the colors, and you can see you get this horrible mess. There's no longer a nice one star of one initial mass gives rise to one evolutionary track. You get all these different pathways you can go down. But you can understand what's going on here. So the things that are brighter than single star tracks are actually merger products. They've absorbed the other star and become more massive. Those that go down are going through Rostov overflow, which is where the stars don't merge, but they lose all their hydrogen envelope, and so they then come off over here and become very hot and slightly less luminous than they were before. So one of the reasons why binaries haven't been used a lot is because people sort of look at them and they go, oh, it's all very complicated. But if you just take a bit more time, you can understand what's going on. One other way of seeing the difference here is to actually then say, let's take these models and actually let's blow them up, because many of these models on this page can actually explode in core collapse supernovae. And if we look at those that are hydrogen rich, when we've still got some hydrogen on the surface when they explode, we can actually see there is a difference between if you assume all the stars are single, as we have it here on the left, and all the supernova light curves, so this is the luminosity of the exploding star over time. You can see that you get plateaus on the left, which have this constant luminosity before falling away in a tail of decay. All the supernovae look very similar if they're all single. Whereas if we put them in binaries, because you get the different interactions, you get a lot of mass loss, you can see you get very mixed. And again, you can think, like the explosions of these binary stars are very diverse, right? And actually, when you look at supernovae in nature, you see something a lot more like those on the right than those on the left. And it's actually what keeps supernova people in business, right? Trying to find and type all these different supernovae. And so this is part of what binary stars do. They change our understanding and make things more interesting. When I say more interesting, I just mean more realistic. Because whenever we look and do this comparison to say, what does single stars predict and what do binary stars predict? It's with the binary stars you actually get a more realistic match to what you see. Because there's more multiple pathways, right, rather than the main general one. So the other thing that exploding binary stars do, if you've ever seen this periodic table by Jennifer Johnson, you can see that there are ways that we can trace back through the universe how different elements are made, where they're made from different sources. And we know that binary stars are also important for like merging neutron stars, which we'll talk about a bit more in a second, and exploding white dwarfs. Okay? So this is stars like our sun in binaries will explode and produce different elements. So you can see here iron, which is important for the hemoglobin in your blood, otherwise we wouldn't be able to carry oxygen around our bodies, comes predominantly from exploding white dwarfs in binary stars. Whereas other elements like gold, silver, platinum, and palladium, and iridium come from merging neutron stars, which are also important. Right? So there are different elements come from different stars, and a majority of the elements only come from exploding binary stars, either in white dwarfs or neutron stars. So that's kind of exciting. It's just also why I get excited about binaries, right? You could argue in some ways that life only exists because of exploding white dwarfs in binary stars, and jewelry only exists because of merging neutron stars throughout cosmic history. So an important question here is, how do we actually include within our models, or like when we're trying to understand the universe, how do we include binary stars? And that's kind of tough. So what we do is we use binary population and spectral synthesis. So this is my code where I've calculated a large number of stellar evolution models. And we know there are uncertainties in stellar evolution, but let's take our best guess. So there's many different types of codes, but people have also looked at binary models in the past and say, well, there's all this extra physics we need to put in, and we're not too sure what it is, but we're taking our best guess. And you hear a lot about multi-messenger observations today, like using electromagnetic and gravitational wave observations to try and understand the same event. We're trying to do the same thing. We're trying to observe our models of stars and how they evolve over their lifetime in different ways, because then you get the more constraints on the physics that you're understanding. There's some other interesting things we're talking about. We've had a couple of versions of this. Our second one is now got 250,000 detailed stellar evolution models. So we actually follow the evolution of our stars in detail rather than treating it approximately, as most of our population synthesis codes do. And this requires like 5 minutes up to maybe an hour to compute some of these models. So that's actually a significant computer time. And BPASS is a suite of codes. So at its heart, it has the stellar evolution models, which is where we're making models of how stars evolve over their lifetime. On top of that, we have a population synthesis code, which works out how many of each different model we should see in nature. And then we also have the spectral synthesis code. And so we actually now have an electromagnetic synthesis code, which predicts what it look like if you look at these stars through a telescope. And we also have gravitational wave spectral synthesis. So that's what we would see from our populations if we're looking at gravitational wave observatories. And again, it's all about trying to take our models as close to observations. Because when you observe something and you try and work out like the temperature of a star, there's assumptions in there because you don't know everything about your observation. But if you try and take your models as far as you can to observe them in the same way that we observe in nature, and make a comparison between your predicted observations and what you observe, you actually get much more firm findings in what you're trying to work out. There's also many papers. We named our codes now after New Zealand animals. Although Elizabeth is making a strong case for having some British animals in there, like the badger. So maybe a future version of BPASS will be called Badger, or Moa, for the one that deals with dust extinction. Our current version is called Tuatara because it's designed to look at older stellar populations beyond 200 million years old. And of course, the Tuatara is a couple of 100 million years old as a species. We also have a new code called Hoki, which is what you can really use yourself if you want to try and understand and use binaries. It's a Python package that has many routines and recipes and instructions on how to try and use binaries to try and understand anything you want to. So it's kind of handy if you want to look up a number about what binary stars do for something. You can, at the moment, do a lot of it with Hoki, and we're trying to add extra information to that as we go along. But you can see the enormous amount of work we've been able to do since finishing our starting to create version 2 of BPAS back in 2016. So we've been really productive because our system just works. Every time we compare our single stars and our binary models, we do better with our binary models and matching the observations. And it's really exciting seeing what other people are doing. So that's an introduction to why binaries are important. Some of the evidence of why binaries are important for exploding stars, and how we use BPAS and what BPAS is. But now I want to take a quick break and think about the big picture. So this is something we've been building up to with BPAS, where for a long time we've been looking at individual resolved stellar populations. But now we're starting to think about how stars evolve across across the universe. So, you know, we can look at individual galaxies, we can look at individual stars in our galaxies, but we want to think across the universe to start thinking about, can we link the stars that were formed back here 10 billion years ago during reionization, when the universe is becoming transparent, to, say, gravitational wave events we observe today? Can we also model and understand the evolution and the nature of the stars and stellar populations throughout cosmic history? Can we also see the rate of supernovae and predict it, because we can actually detect supernovae to quite far distances, all the way back to redshift 2, which is around about somewhere here in the middle of the universe? Can we reproduce that and match that for models, which is a big step up? And the problem here is we need to actually add in an extra ingredient, which is actually to start trying to understand and place constraints on the evolution of the universe. So what we get out from BPAS is, so we're going to look at the rate of supernovae and gravitational wave transients through the history of the universe. And the thing that BPAS produces are these things, which are called delay time distributions. So these are the number of events per massive star formation per year. And so you can see here we have on the right, this is what you'd expect in our galaxy. We expect so many cold-collapsed supernovae in red, so many type 1a supernovae in blue, but also quite a few gravitational wave transients in these different black lines. If we have a less metal-rich star, which would have been formed earlier in the universe, you can see we still get quite a few cold-collapsed supernovae. We get more type 1a supernovae, but we also get some other extreme events of supernovae like long gamma ray burst or pair instability supernovae, and again more gravitational wave transients. But this is only just the number we get per massive star formed at some point in time. To try and work out a rate we can observe, we need to combine it with a cosmic star formation history. So here, this is the number of stars formed per cubic megaparsec, so per volume of the universe per year. And if we multiply this by the number of events we should expect from each star that's formed, we can actually then work out what this is. And we can actually predict the number of events per cubic megaparsec or cubic gigaparsec, depending on what your favorite unit is, versus either redshift, which we can measure quite easily, or versus look back time, so past into the universe. We also need to actually not just assume how much stars are being formed, but also assume something about the cosmic evolution of that time and how the universe is evolving. So it's quite exciting to try and bring all these things together, because not only now are we worrying about stellar evolution, we're also worrying about the evolution of stars throughout the evolution of the universe itself, by trying to look at these events. Now we can compare these model predictions, of course, to observations. And so here we're predicting what the cold-collapsed supernova rate is, the type 1a rate, and also the number of long gamma ray bursts, which is quite difficult. Ashley Crimes, Elizabeth's previous PhD student, who's now a postdoc in Nijmegen, has done a very good paper recently looking at the long gamma ray bursts in more detail. But it's important to get at the type 1a rate, because while they come from white dwarfs, so stars like our sun, they're basically checking that, yeah, our low mass and our physics is roughly right. Whereas our cold-collapsed supernova rate, matching that, is telling you we're producing the right number of neutron stars and black holes at about the right rate. I should note as well, the error bars here are actually quite significant. They're probably bigger than even the observations are estimated, because, you know, it's very difficult to find cold-collapsed supernovae at very high redshifts. But we don't do too badly, right? We're producing neutron stars and black holes in about the right rate, and we're also producing these other types of supernovae at about the right rate. So the question is, with these black holes and neutron stars we're forming, how many are in binaries, how many are producing gravitational wave mergers? And so that's what I can show you in the next plot, where here each panel is for a different type of merger of compact remnant. So here it's double neutron stars, here it's a black hole and a neutron star, here it's a black hole merger. And so the dashed dotted line is an upper limit, the rate must be below that. The solid line is the best estimate, right? And the dashed line is the lower bound. And the colored lines are different B-pass predictions. And so things were varying in the different colors are different amounts of early star formation. So the light blue is more early star formation than in the red line, right? Because if you have more stars formed, you're going to have more mergers. The dashed line has a different type of neutron star kick. So when the star explodes, it gets a momentum kick. You're more likely to bind or unbind the binary depending on that kick. And the solid line is a different initial parameter distribution for the binaries. And so everything's binary in version 2.1. In 2.2, we put in some more single stars and changed the period distribution a bit. And so again, you get more mergers. What's interesting is between these different lines, you can see that the kick affects these things in a different way. So for example, here, the version 2.2 gives you a higher rate than having the Briel kick for the black holes, but for the neutron stars, they give you a much higher rate for neutron star mergers than in the other two. And what's beta? So beta is actually how quickly the universe evolved in metallicity. So this is how quickly stars produced metals to then pollute further stars to make them more or less metal rich. And you can see that neutron stars don't really care about how quickly the universe was evolved, how quickly the universe became metal rich. But black holes do, which is interesting because, of course, if stars are metal rich, they have strong winds, and so you don't get as big black holes. So the black hole merger rate is really sensitive to the metallicity evolution of the universe. So what's great, when we did this study in 2020, you can see that you get something where we assume beta is about 2 for our understanding of the universe. So that's great, that matches with everything, and maybe the rate is actually quite high, so maybe we need this strange kick. The good news is this year we now have new rates because LIGO Virgo have announced their O3A results, and unfortunately the neutron star merger has come down. So here we've just changed the observational constraints, and so now actually we're back to preferring the Beach version 2.2 rate. Again, the metallicity isn't too important. They have possibly detected some black hole neutron star mergers in O3A. So this is the third observing run, first half of the third observing run. And so, but they haven't estimated what the rate is because of 2 events. It's very difficult. I mean, the previous rate for the neutron star mergers was based on 1 event. And over here for the black hole mergers, we've now got a problem. The rates are so low, they're actually pushing us to very high beta values, especially if we believe our version 2.2 results, which we kind of do. So, there's something very interesting going on here, and we're still trying to understand completely what's going on. So what are we working on now to try and understand what's going on? And this is just a quick last bit of a second, just to breeze through some of these. So one thing we're working on is trying different cosmic star formation histories. So I showed you one earlier, but it's actually this one down here in the bottom left. And so the color here is the different metallicities. So how much metal there is in each of the individual stars when they form. So these are all the analytic solutions down here, and these ones up the top are actually from cosmic simulations of star formation. So they're a bit jumpier because they're not average, they're not fit for observations. They're actually from a simulation of how galaxies are forming. And you can see these look very different to those down below. And so this is actually something that's interesting. Maybe we're not predicting the right amount of stars being formed. And so we need to actually look at this quite quickly. And even though we've done it analytically with Petra, Max is going to go in and look into a bit more detail and see how different cosmological simulations change our predictions for the merger rate. We're also trying to look at the host galaxy of the one event we have. The problem is that everyone who's looked at this has only assumed that all the stars are single when they tried to understand it. And so, Andrew Levan has done some work on fitting this host galaxy of the binary neutron star GW170817. And you can see the mass that they form of stars has ages and quite high metallicities. When we've looked at this with our own binary models, we know that the age is probably about right, but the metallicity is very different. And we know from looking at other type of systems, so Elizabeth did this wonderful paper where we looked at older stellar populations before, we can see that BPASS produces a very different age distribution to other single star models that people have used. and also the metallicity of the stars we get out, or the stellar populations we get out from these old populations, is also very different compared to what other people have worked out. So we're still looking at this, we're still trying to understand what the evolutionary history of those stars are, but we'll get to it soon. We're also going beyond just looking at the rate of supernovae. We're trying to reproduce where the gravitational wave events happen, because we know their chirp mass, which is like how massive the two black holes are when they merge, and we're trying to, this is chirp mass along the x-axis here, and mass ratio, so the ratio between the two masses up on the y-axis, and we're trying to understand, can we match those details of the observations? And of course the observations had huge error bars, but you know, we have got this, the darker colors here mean it's more likely to find a supernova in that location, and that's what we're trying to work. So yes, we're trying to understand that mass distribution, and it's, I mean, I could go on about hours because this is really interesting. I've been working on this recently, trying to understand more about the mass distribution, because there's systems here that we are predicting that aren't there. Well, they are there, but we're predicting too many of them. So there's so much interesting physics in here I could go into that I don't quite understand. That's quite exciting. We're also trying to work out when each individual event formed, because it's one thing to predict the rates, but trying to use the systems we observe to understand when they formed. So here we've got a distribution for the first event that was formed, observed, GW 150914, and you can see that it must, so here's the age, when the event rate of the systems of this age peaks in very early times, so it's probably most likely one of the first stars that actually formed because it's so massive. And we can actually also understand the masses, so actually this is the mass of star 1 compared to star 2, plotted on different axes, and we can see how the track goes. So the contours here are the range, and the different contours do mean things, but it's like we can see what the past history is. And so, for example, the first one must have come from a star that was very massive, maybe 100 times the mass of the sun, and about 40 times the mass of the sun, and from a star that maybe it could have actually been quite a high period, maybe like 10,000 days, or it could have been a much shorter period of like only a few days. And so it's this kind of trying to trace back the history and trying for each event work out, for example, where it came from. And here's another one, and you can see it's got a much more messy evolution, and there's much bigger range of possible evolutionary pathways of where it could have come from. And we've got all these different parameters down the bottom as well. One final thing we're trying to do is, I talked a lot about gravitational wave events, but there's one other thing we can get out from our stellar population, right? Because BPASS was not created to model gravitational wave events. It was to try and predict the emission of stars. So if you were to take a spectrum of a galaxy, you would get something that looks like this. So this is a spectrum, or spectral energy distribution of wavelength versus flux of that wavelength. And you can see here the spectrum you see for a normal stellar population, and you would begin up here in the black and evolve down in age as the system gets older. In grey here, we've got just the stars. But one of the things is, if you form a very massive black hole or neutron star, then that can accrete material in an X-ray binary. And if we include that, you get very strong X-ray emission. So here in the colored lines, you can actually see our predictions for X-ray binaries, which is important because we can go to a galaxy, measure its X-ray flux, and say, right, we're observing these stars in supernovae, we're observing their final mergers and gravitational wave events. Can we also predict how much light they're producing when those black holes are feeding? Because one way of actually producing very massive black holes are actually by accreting material. And actually, we go back to this plot. This big blob here is actually because some very massive black holes accrete a lot of material from their still living stellar companion. And when they do that, they produce a lot of X-rays. And there's good evidence to show that our predictions are not too wrong, if that makes sense. But we've been trying to get this paper out for years. It's like 2 years in the running now. I will get back to it and write it because I think it's going to be really interesting to try and put our physics into our binary model and look at it in different ways. And actually what's interesting, gravitational wave transients have really given us a really interesting and unique way of constraining our models, but they've also, the same models have to fit all these other observations. So that was some of the things that binary stars do. I'm sorry, you can't ask me questions. If you have questions, I'd be more than willing to ask them via email, or you can ask Max, who will have some of the answers as well, because he's giving the talk after me. Yeah, it's kind of exciting, and we're getting really close to being able to look at these gravitational wave transients. And when I've looked at the current catalogue, we have 50 of these systems now. And it's really exciting. There's stuff in there that I'm trying to understand, and it's really entwined the way that physics all works together. So it's quite exciting. So anyway, I hope you enjoyed the talk, and I hope you enjoyed talking after me, and have a good afternoon and evening, everyone. Goodbye. Thank you for listening. You should say as well.
Okay. Right. Oh, well, I hope you all enjoyed that talk and saw some linkages there to Max's talk earlier on. Unfortunately, we don't have any questions, so we'll draw this session to a close, and thank you all for attending, and I hope you found it interesting. So it's good night for us. Ka kite anō.